All right, so let's go through this one because I feel like this kind of encompasses everything that we kind of need to know. All right, let's start from the very beginning of when blood is filling in, right? So for example, like let's start here. And we have the AV valve open, right? Which means what? Blood is gonna fill the ventricles. Yeah, it's gonna fill the atria and the ventricles. So blood fills ventricles. Is that okay? Cool. Right. Then you have this P wave. What does that mean? Yeah, like atrial depolarization, right? So atrial depolarization. So what happens when you have atrial depolarization? Atria will contract. Is that okay, Susanna? On board? Yeah, makes sense. Okay. So over here, atria contracts. That's fine. And we kind of like see that here, like the pressure that kind of increases, right? So cool, on board. It's like the last squeeze that they do to put blood inside the ventricles. Okay. Then what happens? Like let's say around here. Oops. Like here. Like these things. Yeah, exactly. Yeah.
For the initial, like, with the AV valve opening, that's like the passive filling of the atria and ventricles.
Yes. So AV valve just stays open. We'll start from that situation because it's a cycle. You got to start somewhere. So that's where we're starting from. AV valve's open, blood's coming in, filling the ventricles. That's fine. Atria squeezes a last bit of blood. Cool. All good. Okay. Then the ventricles start to contract because of the ventricle depolarizations. That's the QRS complex thing we see, right? That's okay, right? All right, so if ventricle starts to contract over here where these two graphs like cross over, what does the crossover mean? So over here, the red is the ventricle pressure, the blue is the atria pressure. So that means what? The ventricle pressure is greater than the atria pressure. Is that okay? Yeah. So if I have like this, I don't know, I'm just gonna draw a very crude diagram of the heart. Let's say this is your, okay. This is like your valve. Things are coming in. It was usually open initially, and sorry, okay. It was initially open, blood was coming in, but now since there's like too much pressure around here, this valves would close basically. Blood wouldn't go out. Okay.
That's the AV valve.
Yeah, that's AV valve. Hey, how are you doing? Good. Yeah, so AV valve is going to close. Is that okay? Cool. And then let's say, okay, the pressure in the ventricle is increasing, it's fine, we're on board. Over here, what's happening? There is also, again, the pressure change, like between the two. So over here, what's happening? The ventricle pressure is now higher than even the aorta pressure. Is that okay? Are you able to see that? Okay. If that happens, then what? Is that okay? Semilunar valve open, that means blood would like gush out into the aorta. Cool. All right. Blood's going out. Cool, cool, cool. I'm happy with that. So if the blood is leaving the ventricle blood volume would start to decrease. And we're kind of seeing that here. Is that okay? Yeah. All right. And then at a point, you're going to have ventricle repolarization. That's the T wave. That would signal the ventricles to relax. Is that fine? Okay. So if the ventricle relaxes, that means the pressure decreases in the ventricles, which is what we're seeing here. Like here, that's fine. And then you have this, again, intersection of the two graphs. That means what? pressure in the ventricle is now lower than the pressure in the aorta. Okay, which means what?
Wait, is it the pressure in the aorta?
No, the pressure in the ventricle is lower. So if you see the
Oh,
red
lower.
is like below. So the pressure in the ventricle is lower than the pressure in aorta. That means what? The valves would, which are like open like this usually, right? They open like this. So if the pressure over here is higher, it would like close. Cool. So semilunar valve closes. All right. And if the semilunar valve closes, AV valve was already closed, things are not moving out of the ventricle. So their volume is going to stay constant, and this is the isovolumic relaxation. Is that okay?
Because the SL valves are closed and AV valves are closed.
Yeah. Both valves are closed. AV valve was closed here. Now SL valves are also closed. So volume is not going to change. Okay. So volume would change. That's fine. Oops. No. Hang on. Okay. Yeah. So if volume doesn't change, and by this time, like the ventricle is also still relaxing, so pressure is falling until this point, where again you have the intersection of two curves, which means the pressure in over here, which one is higher? So the red is the ventricle and blue is the atria. Yeah. So atria is higher than the pressure in the ventricle, which means what? Which valves would open or close first? Atria, ventricle.
The AV valve.
Open? Is that okay? Yeah. And if the AV valve's open, that means what? The ventricle would start filling up again because blood is gonna come trickle in. Okay. So ventricles fill up again. Cool. And the whole thing kind of repeats itself.
Diastole, that's just like quote unquote like the beginning of starting out.
Yeah, we're kind of like starting from like this part is like this part.
Okay, so that's like late diastole.
Yeah.
Okay.
Sorry. No, there's no slides. I'm just writing on it. Yeah. Yeah, sure. Bottom graph as in like this one. That one's for the volume, so like blood volume. Yeah. So if we track blood volume, what's happening? Ventricle is being filled up. When all the valves are closed, there's going to be isovolumic thing happening. Yeah. It's here, right? Okay. Yeah, of course. And then it's ejecting, so volume is different. So this one is the volume stuff. And I guess there's another graph you guys did in the class and also in the problem book, which is like a box thingy. Does that ring any bells?
Oh, is that like the volume?
Yeah, the volume graph, like a box, right? That also kind of like depicts the same thing, but in like just a one graph. Is that something like you want to go over, or are you like okay with that?
Yeah.
Sure. Okay, let me just bring that out. Nope, wasn't here. This one. So yeah, let's very quickly like go over it because let's go over some other important things. Okay, so this one we start from here when the ventricle volume is like the lowest, whatever, and then blood is trickling in, remember, during diastole, right? Blood is coming in, fine, so volume is increasing, pressure is not increasing, so the y-axis is the pressure, that's not increasing because the ventricle is not contracting. That's fine, right? Okay, so the volume is increasing because it's being filled up. Then this part over here is the atrial systole. That means like atria is contracting, squeezing in the last bit of blood. Okay, all right. And then the ventricle starts to contract, but the valves are still like closed. So the volume is not going to change. So this is isovolumic contraction. Yes. Yeah, I think so. Is it called atrial kick? Atrial systole? Just like sure. Yeah, like it's just like the last squeezing of the bit of blood. Yeah. Okay. And then afterwards, remember we talked about like the crossing where like the ventricle pressure has increased so much that it's exceeded the aorta pressure. So the valve opened, the semilunar valve opened. So now the blood's going to be ejected out, which is why the volume is decreasing. Right? So that's why it's decreasing. Cool. Pressure is still increasing. At a point, pressure starts to decrease because they would start to relax. That's the thing we saw in the Wigger diagram as well. And that's when the pressure in the ventricle has fallen now a little lower than the aorta. So the valve would close. So this is semilunar valve closing here. Is that okay? And because all the valves are closed, it's going to be another isovolumic thing. And in this case, it's going to be isovolumic relaxation. That's okay, right? Okay. And then we can like start again filling out blood. In this over here is going to be where the AV valve open. Is that okay? I didn't forget to mention this is where the AV valve would close, right? That's fine. Yeah? Okay. Sorry, got distracted. No, we didn't get distracted, but yeah. Okay, so for the Wigger's diagram, or basically anything to do with the cardiac cycle, any questions before we move on? No? All good? Okay, awesome. Let's move on to thinking about blood pressure. So blood pressure, or like we kind of talk about MAP, just mean arterial pressure. What does that depend on? Yeah, what does that depend on? Cardiac output in? So cardiac output depends on like heart rate and stroke volume. But MAP depends on cardiac output and on TPR. How much do you guys talk about TPR or not at all? Total peripheral resistance. Okay. Okay, no worries. So we'll also keep it light, but just like making sure that you do know what that is and stuff. So, okay. So, because it is important. Anyway, so MAP would depend on cardiac output and TPR. Cardiac output is basically how much blood you're like ejecting out of the heart per minute. So that would depend on how many times the heart is squeezing and how much it is squeezing blood out at each beat, right? So that's basically heart rate and stroke volume. Is that okay? Right? Okay, cool. So let's dive into each of them. So let's say heart rate. What does that heart rate depend on? Heart rate is basically how many times the heart is beating, right? What does that depend on? Question. Like who determines it? Which cells? Yeah, exactly. So like the SA node, the autorhythmic cells, whatever. Okay. Okay. And that is mostly the ones that we're going to be talking about. So you can control that externally. By externally, I mean the brain can, using the sympathetic and parasympathetic pathways, right? The sympathetic, parasympathetic, we went into so much detail about it before the last exam in terms of how they control stuff. So we talked about preganglionic neurons, postganglionic neurons, and the postganglionic neurons would release some neurotransmitters onto the cells, right? So which neurotransmitter is being released for the sympathetic? Epinephrine, right? Like norepinephrine for the neurotransmitter. And if it was like hormone, then epinephrine. Is that okay? All right. So do you guys remember what which receptor they bind to? Yeah, what kind? There's alpha, beta, alpha 1, beta 1. Okay, so in heart it's beta 1. Okay? Just know it. Yeah. In heart it's beta 1, adrenergic receptor, and beta 1 is coupled with, so it's a GPCR, so it has to be coupled with a G protein. What kind of G protein? GS? Yes, perfect. GS. What does GS do? Yeah. Is this visible or too light? Okay, anyway. So yeah, it would increase CAMP, that's fine. What does that do? Yeah, it does. So like PK, right? Yep. And that would phosphorylate, yeah. The T-type channels in this case, which would allow like more sodium and calcium to get in. Which does what? Basically allows the cells to depolarize much easier, much faster. So that would increase like the frequency of action potential. Yes. Okay, we're gonna press chat, that's fine. We're just gonna deal with this one. Oh, okay. I'll have to go back to wait, I know where that is. Hang on. So that was gonna be the cardiac cells. Okay, we'll come back to that very briefly because we are gonna go through that cells. Yeah. Eventually they would like increase the heart rate, right? Is that okay? Yes, no. Okay. Cool. So that's like the mechanism of like how noradrenaline or norepinephrine, sorry, America. Norepinephrine would increase heart rate. Okay. For the parasympathetic, what do they release? Like what yeah, they do. And what does the acetylcholine bind to? Do you remember which receptor? Yeah, muscarinic. Perfect. And in this case, this is an M2 receptor, which is coupled with GI, which means they would do kind of like the opposite, would decrease CMP. So decrease like the phosphorylation of pKa, basically the opposite. So would decrease the I-funny conduction, and that would decrease frequency of action potential, decrease heart rate. Yeah. So nicotinic, ion channels, muscarinic, GPCRs.
Got it.
That's it. That's the difference. Okay. Is this okay till now? Yes. Yeah. They're different because the I-funny. Okay, I do have to go back. Wait. Not here. I wasn't here. Can you tell me which lecture slides that talked about the different cells? It wasn't this. It wasn't this. It wasn't. Yeah. Was it lecture 9? No, it wasn't this one. 8. Yeah. Okay, perfect. So we haven't talked about this. We're talking about this cells over here. So this is the iFunny channels over here, like at the start. If they open, they would make it more like a depolarized sort of state so that it helps the T-type calcium channels to open. So they're all kind of working in one after the other sort of thing. Yeah.
Or this, so that 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 because phosphorus
Yes.
so it doesn't like necessarily like increase that.
It does. It does increase the activity. So I think it's phosphorylates. Does it phosphorize iFunny channels but they do increase IF conduction. Is it just because they're making it come down like sooner? Mhm. Yeah. Okay. Yeah. Yeah. Okay, I see. So in this case, what we're trying to talk about, I'm just gonna take this out just so I can draw on it. So the iFunny channels, and normally they would spontaneously open just because these are like spontaneous activity that just happened. So because we're making it depolarize like faster or easier to depolarize, it's just going to like this thing is just gonna happen like sooner, sort of thing. I don't think the iFunny channels are phosphorylated. They're just like how do you say it? Like there's more ion moving in and out of the iFunny channels. Does that make sense?
Because the T-type are more.
They're more open, yes.
Okay.
So like conductance is just like allowing more ions to move through. So the root of the thing is you kind of have to get to like the points such as okay, like mentioning these things. I'm just gonna circle them, which are like let's say would carry points. These things would carry points, knowing which receptor, which neurotransmitter, what receptor are they binding to, what G proteins those are, phosphorylating T-type calcium channels or something, so increase entry of calcium. Like what is happening to the iFunny conductance, those things, and in the end that it's increasing or decreasing heart rate. Those are important to mention. Does that make sense? Sorry. Yeah, it increases. I didn't write it, but funny conductance increases. Is that okay? All right, let's move on. So that's with the heart rate. So we can influence heart rate just by influencing the SA node, autorhythmic cells, whatever. What's happening with stroke volume? What does stroke volume depend on? Yeah. Sorry? Yeah, it does depend on venous return, right? Because why does that happen? So whatever blood is going to be squeezed out, it's going to be depending on how much blood came in, right? So the end diastolic volume. So it would depend on that. So that's the venous return, whatever blood has came through. And it's like the hard muscles are like elastic. So if you like stretch them more, it will like squeeze more. So that's the Frank-Starling law, right? Is that okay? Any questions until then? Okay. So venous return. If venous return increases, stroke volume increases, blah, blah, blah. What does venous return depend on? Sorry, Mahir, I'm taking a little bit of time because we started late as well. Yes, what does the venous return depend on? Just maybe if you have more blood, so blood volume, for some reason, if your blood volume has increased, which is something you're going to talk about in kidney, or just like skeletal pump. Yeah. Because you have like muscles in your legs which can like squeeze, and that squeezes up blood. Okay. And respiratory pump. So all these kind of help blood return back to the heart against gravity. I was gonna do a cool case on that, but like we don't have time. All right. And the other thing is actually sympathetic nervous system also affects it. But maybe we won't talk about that because I guess you guys didn't learn that. But yeah, so those are things that affect venous return. That's fine. You can directly affect stroke volume by the sympathetic nervous system. Is that something we talked about, right? So sympathetic nervous system can directly influence the contractility of the heart. So that would be contractility of the myocardial cells. Okay. So how does it do it? Again, you have norepinephrine binding to beta-1 receptors, similar pathway, just increasing CAMP. They would phosphorylate two things. In this case, they would phosphorylate the L-type calcium channels and would increase the open time so that more calcium can enter, increase the contractility of the heart, like make it contract. The other thing it does is it also phosphorylates something called phospholambin. Is it lambin? Yes. Okay. Which actually increases calcium ATPase activity. That's something you guys talked about in class, and would kind of help mop up the calcium away so that they can like quickly relax as well, and they can like contract again. So overall, this increases contractility of the heart. So it squeezes out more blood. Is that okay? Yes. Yeah. Yeah. Because there is none in the heart about the GQ. So that one would have to be, I think, alpha-1 receptor, and that to do with TPR, and we will probably not talk about that. Okay. Does stroke volume get affected by parasympathetic? Question. Yes, no, yes, no. Okay, who says yes? No. Okay, who says no? You gotta have one opinion. Okay, it doesn't. Okay, so stroke volume directly is not affected because the contractility of the heart, like basically the myocardial cells, don't have the muscarinic receptors or the parasympathetic. Is that okay? Yeah. So the myocardial cells don't have any parasympathetic like receptors, like the acetylcholinergic receptors for parasympathetic. So it doesn't get affected. Yes. Yeah. I think the phosphorylate. I'm just gonna do phosphorylate here. So that, yeah. Is that okay? Yeah, they phosphorylate both. Yeah. Yeah, perfect. What receptor, what neurotransmitter? What is like increasing CAMP, which is like directly connected to that. So this is gonna be GS as well. Same thing. And L-type calcium channel, increase open time. I don't know if you have to remember this word, but basically increasing contractility, increase in stroke volume. Those are important. Yeah. Yes. Is that okay? Till now.
Sympathetic.
Yes. Okay.
The myocardial cells are affected by increasing
They're not affected by parasympathetic. They're affected by sympathetic. Okay. Is that okay? So in a nutshell, MAP, if you want to increase like blood pressure for some reason, you can increase heart rate, or you can use increased stroke volume, or you can use increased CPR, but we haven't talked about that. And if you want to increase heart rate, basically if your brain wants to do that, they would increase sympathetic, they would decrease parasympathetic. And that would increase and decrease heart rate. And if you want to increase stroke volume, this is the pathway you take for that. Okay. Want to talk a little bit more about the blood pressure regulation, but I don't have time. Okay, go for it. Feel free to join did you join the Zoom?
Yeah.
Perfect.